T-minus 10, 9, 8,
The clock is operating. We're underway.
Tranquility Base here.
Endeavor, go.
T-minus 10, 9, 8,
The clock is operating. We're underway.
Tranquility Base here.
Endeavor, go.
T-minus 10, 9, 8,
The clock is operating. We're underway.
Tranquility Base here.
Endeavor, go.
T-minus 10, 9, 8,
The clock is operating. We're underway.
Tranquility Base here.
Endeavor, go.
T-minus 10, 9, 8,
The clock is operating. We're underway.
Tranquility Base here.
Endeavor, go.
15, 12, 11, 10, 9, 8, 7. We have a go for main engine start. 4, 3, 2, 1. Booster ignition and liftoff of Space Shuttle Endeavour on a 21st century mission, placing Earth back on the map.
Roll for Roger, roll, Endeavor.
Houston's now controlling. They were rolling on a course northeast away from the Kennedy Space Center toward an orbit that will take it above 95% of the world's population during its mission. Endeavor speed already 300 miles per hour. Altitude 1 mile.
T-minus 10, 9, 8.
The clock is operating. We're underway.
Tranquility Base here.
Endeavor, go.
T-minus 10, 9, 8.
The clock is operating. We're underway.
Tranquility Base here.
Endeavor, go.
And mass power will come on our mark. 3, 2, 1, mark.
Copy. And Houston, we're showing movement of the mass. Copy, we see it.
We can now see a view of the outboard antenna as it's beginning to extend out over the port sill of the Space Shuttle Endeavour's payload bay.
T-minus 10, 9, 8.
The clock is operating. We're underway.
Tranquility Base here.
Endeavor, go.
T-minus 10, 9, 8.
The clock is operating. We're underway.
Tranquility Base here.
Endeavor, go.
T-minus 10, 9, 8.
The clock is operating. We're underway.
Tranquility Base here.
Endeavor, go.
T-minus 10, 9, 8.
The clock is operating. We're underway.
Tranquility Base here.
Endeavor, go.
T-minus 10, 9, 8.
The clock is operating. We're underway.
Tranquility Base here.
Endeavor, go.
T-minus 10, 9, 8.
The clock is operating. We're underway.
Tranquility Base here.
Endeavor, go.
I'm happy to say we've made a new agreement with our colleagues in the National Imagery and Mapping Agency, part of the DoD. They're our partners in the Shuttle Radar Topography Mission, to allow our scientists and engineers and the public too, to a large extent, to have special early access to some of the Shuttle Radar Topography Mission data, the digital elevation maps that we have now for the 80% of the landmass that we're able to map from the shuttle orbit. It's significant because our data processing plan is to go continent by continent and process all the data that we acquired. Those will be available to scientists and the public in about a year. We've made a special arrangement here now because our scientists are kind of anxious and they're really waiting to get their hands on the data to process small sections of data, individual sites from our principal investigator's request and make those available basically immediately. What we produce from this mission are called digital elevation maps. They're digital, so they have all the reproducibility and precision that's implied by that name. They're elevation maps, which means that they are three-dimensional in nature. We made an actual hologram of nearly the entire surface of the Earth. These are used in geology, geophysics, in mapping earthquakes, studying volcanoes, and also have quite a number of uses sort of in the civilian world. For example, making virtual displays that pilots can have in cockpits that will tell them exactly what the outside world looks like in case they can't see outside because of darkness or bad weather. Well, we had previously released data for the United States. We have now have agreed to release data from basically anywhere in the world. And you know, a lot of the world is previously not really very well mapped. The Earth is about 40% cloudy on average. Those clouds are distributed primarily around the equator. So there are large areas of, for example, northern South America, Central Africa, and the Western Pacific, where there are very poor or basically no elevation maps pre-existing. So now we're going to have access to that kind of information for pretty much anywhere in the world. Our scientific investigators have been sending us requests for processing certain areas of interest. What they'll do is designate a latitude and longitude and extent, typically a few hundred kilometers. We take those requests, put them in our computer in our processing queue, and after about a month, or it takes about a month or two to get these data through the system, we will complete sets of data formatted in certain specific ways and deliver those to our investigators. In the large-scale processing, we plan to have, we're going continent by continent. We should have North America completed by the early part of this summer of 2002, and the whole world completed and delivered to NEMA by the end of 2002. There'll be another additional step there where our partners in the mapping agency will apply all that professional mapping skill and techniques to edit the data and bring it in conformance with national mapping accuracy standards. That should take a few more months. So by about the middle of 2003, all of the data for the 80% of the world's landmass that we map should be available to the public. The data that we're delivering to our PIs are digital elevation maps, and they're in kind of a raw form. They haven't been edited, they haven't been gone through all the finishing steps that one would normally apply to make a map. They're really research-grade data, and they're intended for use by researchers for scientific and technical purposes. If you come to our website at JPL and look for SRTM data, what you'll see are products that we derive from those, shaded relief maps, contour maps, various kinds of visualizations that make the data more easily understandable by human beings. The Shuttle Radar Topography Mission was so successful, we accomplished basically 100% of the objectives of the mission and the flight, and the data are just perfect. So there's no real reason to fly it again. However, we do have plans for the future. We have a satellite in work that will be in orbit all the time acquiring data like this that can measure not just the topography, but very subtle changes in topography at the scale of just a few centimeters. This is very exciting because these kinds of changes we think are precursors to volcanic activity and particularly earthquakes. So if this provides a data source by which we could eventually perhaps actually predict earthquakes, it would be a really fundamental breakthrough. The method we use to detect these very subtle shifts in the crust of the Earth is by comparing, or what we call interfering, two separate radar images. But to do that really precisely, you need a pre-existing digital elevation map. That's exactly the kind of thing that has not existed previously for most of the world, but now when we process the SRTM data, we'll have it. Yeah, the SRTM instrument was built primarily of leftover hardware. We'd had a series of imaging radar flights on the space shuttle, 4 to be exact. What we did was take the 26,000 pounds of hardware that was left over from 2 data flights in 1994, fancy it up a little by adding the extendable mast and additional antenna for interferometry, and use that to map the world. This made it an extremely cost-effective experiment. The amount of bang per buck we got from SRTM is just enormous. The total cost was maybe 10 or 20% of what it would have been by building a satellite anew. Well, one of the important applications of digital elevation maps is in wireless communication. If you're going to decide where to put a communication antenna, it's a very difficult topic, problem, unless you have digital elevation maps, which times comes very easy. Now, in the United States, we already have lots of communication infrastructure in place. We could really live without cell phones. But in the third world and developing nations, wireless communication is really important because they don't have this pre-existing infrastructure. So the existence of wireless broadband communication systems is very important. These are exactly the places where we don't have pre-existing digital elevation maps. So this will be a real boon in those parts of the world. Digital elevation maps are especially useful in planning for disasters, flooding, earthquakes, volcanic eruptions, and so on, because you can use them to model, to plan and predict where floodwaters will go, where mud flows will go, which are a common occurrence in volcanic activity, where lava flows will go, even how fires will burn in forest fires because they're controlled by topography and by wind. Well, if you have the digital elevation data, you can be prepared. For many parts of the world, they don't have this kind of information and they don't have that kind of planning ready. So when these things occur in other parts of the world, sometimes they're much more catastrophic than they would have been in the United States. Well, maybe we can help mitigate that now once we make these data available.
T-minus 10, 9, 8,
The clock is
7,
operating. We're underway.
Tranquility Base here.
Endeavor, go.
The SRTM mission goal was to map all of the Earth that we could reach with the space shuttle at higher resolution in a three-dimensional topographic sense than we've ever been able to do before. And that means that anything that requires a good map, like pilots flying into places they've never seen before, they need a map to know where they're going, volcanic flows of areas that are mountainous, watershed, determining where water's going to go. If you build a new dam, what's it going to do to the local water control? Firefighters in mountains that need to know where the winds are going to flow. There's an enormous number of applications where you need to know the shape of the terrain. And I personally believe that this mission will quite possibly be the most single significant mission we ever have or ever will fly in space, because a map that everybody on the Earth can take advantage of is just enormously valuable. There were several times during the flight that stick in my mind, very special memories. We were a dual shift flight, so half the crew was working when the other half was sleeping so that we could map 24 hours a day, which meant that there were a lot of times I would get up and be able to see something really significant, or I would know that on this shift I was going to see something that was really special that maybe the other shift wasn't going to get to see, and I have some of both of those memories. The biggest one when I woke up to see something new was this mast that had the outboard antenna on it was deployed while I was asleep. To get a three-dimensional map, you have a radar in the bay and a radar out on a long boom, 60 meters long, about 200 feet, so that you get a stereoscopic effect. That's how you get the 3D measurements. And this long boom was deployed while I was asleep. So I got up and, of course, went flying up to the flight deck to see how everything had gone. And you could see this thing out the commander's window with the mast all the way extended in the radar at the end. And it has all these cables wrapped on it, electrical cables that contain the power and data for the outboard antenna. And it looked like a Christmas tree because it had all the little bays and stuff. It was just beautiful. Because when I happened to go up there, it was in the bright sunlight. It was just gorgeous. And I was so excited to see that it had all gone out and we were ready to start mapping. One of the other ones was it just happened that the longest pass, as we go around the Earth, different parts of the Earth come under us, and the path for a radar track is going to run from shoreline to shoreline. So how long any individual path is just depends on the geometry at the time. The longest path was over Africa and Asia. So we got one from the southwest corner of Africa up through the Mideast over Asia. And I happened to be on duty when that pass happened. And to watch out the window as all of this Earth goes by and know that we're mapping all of this for all those people to help them better live and grow crops and deal with the weather was just really exciting and special. I was on duty when we tried to stow the mast, and for those that were watching the mission, the mast stopped about 3 inches short of fully stowing, and we couldn't bring it home unless it was fully stowed because it was too dangerous. We either have to throw it overboard, do a spacewalk, something to get it stowed. And it was, the special part about that is to have the ground team, to know the ground team is working like mad to come up with alternate solutions for us. And sure enough, we tried 4 different things, and on the 4th attempt, it closed like it was supposed to. And it's fun to be part of a team that works that closely together and is so creative and focused on solving a problem.
What we produce from this mission are called digital elevation maps. They're digital, so they have all the reproducibility and precision that's implied by that name. They're elevation maps, which means that they are three-dimensional in nature. We made an actual hologram of nearly the entire surface of the Earth. These are used in geology, geophysics, in mapping earthquakes, studying volcanoes, and also have quite a number of uses sort of in the civilian world. For example, making virtual displays that pilots can have in cockpits that will tell them exactly what the outside world looks like in case they can't see outside because of darkness or bad weather. Well, we had previously released data for the United States. We have now have agreed to release data from basically anywhere in the world. And you know, a lot of the world is previously not really very well mapped. The Earth is about 40% cloudy on average. Those clouds are distributed primarily around the equator. So there are large areas of, for example, northern South America, Central Africa, and the Western Pacific, where there are very poor or basically no elevation maps pre-existing. So now we're going to have access to that kind of information for pretty much anywhere in the world. The SRTM instrument was built primarily of leftover hardware. We'd had a series of imaging radar flights on the Space Shuttle, 4 to be exact. What we did was take the 26,000 pounds of hardware that was left over from 2 data flights in 1994, fancy it up a little by adding the extendable mast and additional antenna for interferometry, and use that to map the world. This made it an extremely cost-effective experiment. The amount of bang per buck we got from SRTM was just enormous. The total cost was maybe 10 or 20% of what it would have been by building a satellite anew.